Hello, class. Since I'm not at school today, what we're going to do in class is I've recorded this lecture, and what I'd like you to do is listen carefully to it, take notes while I am giving the lecture. I will ask you, we'll pause the lecture at certain points, and you'll take some more notes. And by the end of the lecture, you should be able to complete that one homework worksheet that I handed out last week called the Electron Configuration Practice. So the goal here is to be able to complete that worksheet, and that worksheet will be due tomorrow on Tuesday. The topic of our lecture today is what we started last Friday about atomic orbital theory. We're talking about atomic orbitals, and we're learning how to write electron configurations. Keep in mind we already performed an inquiry activity about electron configurations to make ourselves familiar with the patterns that we see and how we go about writing them. So we already talked about, according to Schrödinger, Schrödinger discussed how electrons behave and how they circle nuclei. And he said they circle nuclei not in orbitals like planets, but in regions of spaces where electrons are likely to be located. These are called atomic orbitals. Each energy level can be made up of several sublevels, which is made up of different orbitals. And this will all make sense in a second. From our inquiry activity last week, we saw that our periodic table is separated into different blocks. These blocks are all about orbitals. They separate based on orbitals. We see the S block in the first two columns of the periodic table, the P block in the next on the right-hand side in the 6 columns on the right-hand side. We see 10 columns in the middle, known as the D block, and 14 columns set off to the side, called the F block. These are all different atomic orbitals, and they all mean something, and we'll talk about those orbitals in a second. So the orbitals that we're talking about, again, are regions of space where electrons spend their time, and they move around the nucleus here. And we see S orbitals, P orbitals, D orbitals, and F orbitals. I'm drawing over that. You can see that they all have different shapes, which means that the electrons move in S orbitals in the spherical shape. In P orbitals, sort of like a peanut kind of shape, sort of an oblong kind of shape. If you imagine a balloon twisted in the middle. The D orbitals and the F orbitals get quite complicated, and we'll only speak about them very quickly. To begin with S orbitals, we see that the shape of S orbitals is a sphere. So if you were looking at electrons moving in an S orbital, those electrons could be moving anywhere in this sphere. And so there's a great probability that the electrons occur in this space, but nowhere else outside that space. So that's what it means for the S orbital to have a spherical shape. I'd like you to take some time in your notes now to draw an S orbital and label it S orbital. And then after you've drawn an S orbital, we can label that a 1s orbital. That is to say, it's an S orbital that takes place in the first energy level. Then I'd like you to take some time and think and predict what a 2s orbital looks like, and how a 2s orbital would be different than a 1s orbital. Pause the video and take some time to do that. Hopefully you've paused your video, and let's just quickly review. S orbitals, let's use my pen here. S orbitals, okay, looks like a sphere. And so if we were to call it a 1s orbital, we'd draw a simple circle that represents a sphere. A 2s orbital, on the other hand, is a sphere as well. It has the same shape, except it's a little bit bigger, because each energy level will be a little bit, a 2s or a second energy level would be a little bit bigger than a 1s orbital. And then you can imagine a 3s orbital would be bigger still. So they're still spheres, they still look the same, except the sizes are different. Make sure you have that in your notes, please. Before we move on, we have to remind ourselves that this sphere that we represent with a circle is taking place in 3 dimensions. And so to represent those 3 dimensions, we're going to draw coordinate axes. We'll draw one axis, a second axis, and a third axis. Okay, and so this just looks sort of like what you'd see in math in a coordinate plane, except now instead of having just an x-axis and a y-axis, the x-axis would be going side to side, the y-axis going up and down, and then we're going to call this next axis a z-axis. The z-axis is sort of hard to imagine. It's an axis that actually you have to imagine it going into the page and coming out of the page. So it's going front and back. And we can represent that sort of two-dimensionally with this. It looks like a diagonal line, but we have to imagine spatially that it's going into and out of the page. And so our our s orbital would be a sphere that would be three-dimensional. I'm saying this now to prepare us for the next orbitals, the p orbitals. So p orbitals don't have a spherical shape like an s orbital. Here's our s orbital here. A p orbital has what you might describe as a sort of a peanut kind of shape, or if we can imagine a sort of a balloon for balloon animals that is twisted in the middle. And so we see it's got this sort of oblong kind of shape. And because it's happening, these are occurring in 3 dimensions, we will have what we'll call a px orbital. That is a p orbital that rests itself along the x-axis of our coordinate plane. A py orbital that rests itself along the y-axis, and then a pz orbital, okay, that rests itself along the z-axis. And so if we were to draw or depict those p orbitals on all axes at the same time, we would see something like this. So this would be a representation of all 3 p orbitals. Now again, it's important to know the shape of the p orbital and that they have different configurations in the x-axis, y-axis, and z-axis. So just like with our s orbitals, I'd like you to take some time and in your notes draw 3 p orbitals. Make sure to draw the p orbitals on the x-axis, the y-axis, and the z-axis. Then I'd like you to draw all 3 p orbitals on a single xyz axis. And it would probably be helpful for you while drawing your orbitals is to also draw your coordinate plane. Okay, so take some time to do that, please. So to review, let's draw some p orbitals. If I can spell correctly. P orbitals. All right, let's draw our xyz axis, x, y, z. Let's draw another one, x, y, and z, rather, and then a third one, really y, x, and z, and then one more, fourth one, y, x, and z. Now it's not going to be perfect by any stretch, but here we go. So to draw our px orbital, you draw it along the x-axis. And again, it looks sort of like a figure 8, but we have to imagine that it's taking place in 3 dimensions, so it's sort of globular. So this would be our px, p sub x orbital. Here's our p sub y orbital. Our p sub z orbital. We'll draw that. And then if we put them all together, we have our p sub x. I might have to squish these in. P sub y, and then our p sub z going into the page and out of the page. And so this would be our p, x, y, z orbitals. Okay, good. Let's move on. Now I won't have you draw these because they're much more difficult to draw in 2 dimensions, but these are d orbitals. D orbitals sort of look like p orbitals, but they're a little bit more complicated. We see the shape of a d orbital looks like a p orbital, but almost doubled. And so as you can see, they take place in sort of a plane. The plane in this one looks like it's a d orbital on the yz plane, a d orbital on the xz plane, on the xy plane, and we call this one on the dx2 y2 plane, and then this crazy looking d orbital that looks like a p orbital with a donut around it, but this is the 5th d orbital. We call it the dz2 plane, or dz2, orbital. I'm not going to ask you to draw these, but I will expect you to recognize their shapes. Similarly to the d orbitals that are complicated, the f orbitals get even more complicated than that. Again, we have to remember that these atomic orbitals are spaces or regions of space where electrons are likely to be. So if an electron is likely to be in a d or, for example here, an f orbital, we find that there is a likelihood that the electron can find itself in any one of these spaces. In fact, they can find themselves in any or all of that space, and they travel to and from all of those spaces, but they don't find themselves in between those spaces. Don't ask me why that's true. That's just how electrons behave. So f orbitals look pretty crazy. Again, I won't ask you to be able to draw all of them, but it's important that we know that there's 1, 2, 3, 4, 5, 6, 7 f orbitals. There are 5 d orbitals. There are 3 p orbitals, and there's 1 kind of s orbital. So having an understanding of the shapes of the orbitals and how many of each type of orbital there are will help us in assigning electron configurations. That is to say, what an electron configuration is, and you might want to copy this definition down. An electron configuration is the ways in which electrons are arranged in atomic orbitals. And if we know how they're arranged, we can have an idea of how those electrons behave, or where they move, or where they're located. In order to assign electron configurations, however, we have to be aware of at least 3 rules or 3 principles. The first principle, or the first rule, that is important in assigning electron configurations is what's known as the Aufbau principle. So make sure to have this in your notes. The Aufbau principle is pretty simple. All it says is that electrons fill atomic orbitals at the lowest energy level first, before they enter higher energy levels, which is to say, electrons will occupy the first energy level before the second energy level, and the second energy level before the third energy level, which is another way of saying you're not going to find electrons in high energy levels before they fill low energy levels. Electrons want to be in the lowest energy state possible. When we drew Bohr models, we said that there were only 2 electrons allowed in the first energy level, and 8 electrons in the second energy level. That's what? 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. Is that 8? I can't count. I'm losing my mind. All right, 8 electrons in the second energy level. But we didn't answer satisfactorily why we have 2 in the first energy level and 8 in the second energy level. Well, atomic orbital theory helps us explain why that's true. Let's take a look. And we can use the Aufbau principle to help explain. So if we look at atomic orbitals, we can see that the 1s orbital has the least energy. It's the lowest energy state. So electrons in the 1s orbital have the least amount of energy compared to all of the rest of electrons in a particular atom. A 2s energy level, or 2s orbital, has lower or higher energy than the 1s, but less energy than the 2p. Remember, there are 3 different configurations for p orbitals, so we have 3 different orbitals. So we might have the px, py, and the pz. And the 2p orbitals have higher energy than the 2s, but lower energy than the 3s. The 3s, again, is a single orbital. The 3p orbitals, again, have 3 different sublevels, but they have higher energy than the 3s. Notice also here, quickly, look at the 4s orbital. Compare it to the 3d orbital, and we see that the 4s orbital actually has lower energy than the 3d orbital. Okay. What we can conclude then is that electrons will occupy the 4s orbital before they occupy the 3d orbital. And we'll take a look at that in a second. But coming back to that Bohr model, the reason why we fit 2 electrons in the first energy level is because the first energy level is only made up of an s orbital, and the s orbital can only fit 2 electrons. The second energy level is made up of a 2s orbital and 3 2p orbitals, which is to say we'll fit 2 electrons in the 2s orbital and 2 electrons in each of the 2p orbitals, for a total of 8 electrons. And we'll move on from there. So the off-ball principle tells us that electrons occupy the lowest energy levels first before they occupy higher energy levels. And so there is a good diagram to use, and I encourage you to draw this yourself. So pause the video in a second to draw this diagram, but let me explain what it shows you first. What we see here are all the orbitals, the s, p, d, and f orbitals, and we see each energy level. So the first energy level only has an s orbital. The second energy level has s orbitals and p orbitals. The third energy level has s, p, and d orbitals. The fourth energy level has s, p, d, and f orbitals, as do the fifth, sixth, and seventh energy levels. This diagram gives you some arrows here, and these arrows indicate the order in which electrons fill the orbitals, which is to say, our arrow right here shows us that the first orbital to fill electrons is the 1s orbital. Our second arrow says that the 2s orbital is the next orbital to fill. This arrow shows us that the 2p orbital follows next, followed by the 3s orbital. The 3p orbital is next, and here's where it gets tricky. After the 3p orbital and before the 3d orbital, our 4s orbital is filled. All right, we said that's true because 4s orbitals have lower energy than their 3d orbitals. 4p orbitals follow the 3d orbital, followed by the 5s, and followed by 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5f, 6d, 7p, and so on and so forth. So this diagram here shows us the order in which electrons fill atomic orbitals. And underneath this table, you see 1s is filled first, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, and so on. If we can remember if we can remember how to draw this diagram, you'll have no problem assigning electrons to the correct orbitals in the correct order. So to repeat, the off-ball principle says that electrons fill lowest energy levels first. Now the second principle that we'll talk about is called the Pauli exclusion principle. The Pauli exclusion principle says that a single atomic orbital, and I've already referenced this, a single atomic orbital can hold at most 2 electrons. So no orbital, no s orbital, no p orbital, no d orbital, or f orbital. Regardless of shape, no orbital can hold more than 2 electrons. And it's important for us to also recognize that electrons are spinning, and as they're spinning, they're moving around. However, each electron in a given orbital has a different spin. We call one spin an upspin and another spin a downspin. And you'll see that an upspin is really just simply a counterclockwise spin, and a downspin is simply a clockwise spin. But in atomic orbital theory, we call it an upspin and a downspin. So every orbital can have an electron with an upspin, and every orbital can have an electron with a downspin. But ultimately, at most, it can hold 2 electrons. So part of drawing or assigning electron configurations is also to be able to draw electron orbital diagrams. These electron orbital diagrams, as we saw previously, when we represent a 1s orbital, we'll represent that orbital in the form of a box. And that box can hold electrons, but according to the Pauli exclusion principle, the box or the orbital can hold at most 2 electrons. Given hydrogen only has 1 electron, so that electron we can arbitrarily say has an upspin. But if we're looking at the electrons in helium, helium has 2 electrons. So in its 1s orbital, it will have an electron with an upspin and an electron with a downspin. Again, every orbital can have at most 2 electrons, and every electron must have a different spin. So every orbital can have an upspin electron and a downspin electron. That's a pretty simple principle, the Pauli exclusion principle. The third and final principle, or the rule, that we will be discussing is what's known as Hund's rule. Hund's rule says that all orbitals in an energy level is singly filled with one electron before any one orbital is doubly occupied. What we have to remember is that we have to remember that electrons have a negative charge, and that if we take two electrons with another negative charge, those electrons do not want to be very close together, because we know that two negative charges will repel each other. And so electrons want to be as far apart from another electron as can possibly be. What that results in is what we call Hund's rule, meaning that electrons will fill their own orbital by themselves before they have to match up with a second electron. So let's take a look at how we recognize this. Again, since electrons are negative and two negative charges want to be as far apart from each other as possible, when we're drawing the electron orbital diagram for, let's say, for nitrogen, what we'll do is we'll fill the 1s orbital with an up electron, the 1s orbital with a second down electron. We'll fill the 2s orbital with an up and a down. And then when we fill the 2p orbital, we've got 3 electrons left, because nitrogen has in total 1, 2, 3, 4, 5, 6, 7 electrons. With the 3 electrons left, the Hund's rule tells us that we have to fill each orbital, the 2px, the 2py, and the 2pz, each with 1 electron before we can fit another electron, for example, into the 2px. So if we look at this diagram here, we see that this orbital diagram was filled out improperly. This is incorrect, because while we filled the 1s and the 2s orbitals fine, what this person probably did was they filled in the 2px orbital with 2 electrons, and then they had one more with a 2py. But this violates Hund's rule, because we filled the 2px orbital before we put any electron in the 2pz orbital. And we cannot have we can't have 2 electrons in a given orbital before we fill all of the orbitals. So this one, the 2pz orbital, needs to be filled before a second electron is put into the 2px orbital. And this diagram shows something similar. We see a correct version and an incorrect version of the electron orbital diagram for oxygen. That's a terrible O. Let's try that again. For oxygen. There we go. Okay, so let's take a look at the incorrect one first. Incorrect one says, let's fill our 1s with an up and a down, 2s with an up and a down. All right, that's 4 electrons in total. We have 4 more to go, because oxygen has 8 total electrons. The incorrect version would say, let's just fill our 2px with 2, our 2py with 2, and our 2pz will be left blank. That is incorrect, because Hund's rule says that all orbitals need to be filled with 1 electron before a second electron can fill another orbital. So if we look at the correct version, we see our 1s orbital being filled properly, our 2s orbital, and the correct version, the correct way of filling our 2p orbitals would be our 2px, 2py, 2pz, and we've got 1 electron left, so it has to fill that 2px, and that it'll be a down electron, or down spin electron. So we have the Hund's rule, we have the Pauli exclusion principle, and we have the Aufbau principle that helps us generate electron configurations. So let's talk about writing electron configurations, and after that we'll talk about how we fill in electron orbital diagrams. This image, or this diagram, should seem somewhat familiar from our inquiry activity. What we see here is we're writing the electron configuration for helium, right? And so obviously when we write the electron configuration for helium, we'll label it as helium by writing helium's atomic symbol. And then we want to, when we draw electron or write electron configurations, we'll start by indicating the level. And if we're talking about the first energy level starts out with an s orbital. So we start with a level, then the orbital, then our superscript represents the number of electrons in that orbital. So we know that every orbital can hold at most 2 electrons, And since helium has 2 electrons, its 1s orbital has those 2 electrons. It is filled. And so as we continue to write electron configurations, you'll begin to see the patterns that we use with regards to indicating how many or the number of electrons in each orbital. So in order to practice drawing electron configurations, we have to first draw electron configuration orbital diagrams. All right, so this is the first step. So if I've asked you to draw or to write the electron configuration for sodium, we first want to draw the orbital diagram. And so this is the diagram that we saw earlier in the lecture, and it shows us the order in which orbitals are filled. So remember, we start with 1s, 2s, 2p, 3s, 3p, 4s, then 3d, then 4p. So let's take a look. We know that sodium's atomic number is 11. That means it has 11 protons and therefore 11 electrons. Let's fill these 11 electrons in. Okay, so we start with our 1s with an up electron, and then we fill it up with a down electron. The 2s is filled with an up and a down electron, so that's a total of 4. We have 7 electrons left. Our 2p orbital, remember, we're filling 1 electron in each orbital before we put a second electron there. So a 2p orbital is we've got an electron in the 2px, 2py, 2pz. All right, 2px again, 2py, 2pz. That's a total of 10 electrons. We've got 1 electron left, and that will go into the 3s orbital. Okay, notice I can draw arrows. It's also easiest to draw our arrows as some kind of half arrows. But this is in total our electron configuration orbital diagram for sodium. And so if I were to now write the electron configuration, I'd say that sodium has an electron configuration of 1s2, because there are 2 electrons there, 2s2, 2p, and there are 6 electrons in p, 2p6, and 3s1. That would be the correct electron configuration for sodium. Let's do another one with chlorine now. Chlorine has an atomic number of 17, so it has 17 electrons. Okay, so our 1s, 2s, 2p, again, notice how I'm filling in the 2p. That's a total of 10. 3s, and that's a total of 12. We have 5 more electrons here. So we go our 3p, and we've got 2 electrons left, and there we go. That's our total orbital diagram for chlorine. So let's draw it out, or write it out. Chlorine has 1s2, 2s2, 2p6, 3s2, 3p, and there are 5 electrons in that 3p energy level. So here's a total electron configuration for chlorine. What I'd like you to do is I'd like you to try drawing the orbital diagram for magnesium on your own, and pause the video. Hopefully you've paused the video and recognize that magnesium has 12 electrons. And we fill this in with 1s2, 2s2, 2p6, 3s2. Alrighty, so we draw it and write it out. 1s2, 2s2, 2p6, 3s2. Fantastic. All right, and so here's our magnesium element, and now let's try the ion for magnesium. A magnesium ion has a +2 charge, and if we recall carefully, a +2 charge means that it has 2 more positive charges, but it's still magnesium, and magnesium will always have 12 protons, and if it has 2 more protons than electrons, that tells us that a magnesium ion has actually 10 electrons. So if we're drawing the electron orbital diagram for magnesium ion with a +2 charge, we're drawing it with 10 electrons. So here we go. Let's draw it with 10 electrons. And I'm done. So magnesium ion is 1s2, 2s2, 2p6. And that's it. So notice that the electron configuration for magnesium is different than the one for magnesium ion. So finally, I'd like you to try out on your own the orbital diagram for oxygen ion. And oxygen ion has a -2 charge. So pause the video and try out on your own oxygen ion. All right, hopefully you've paused and recognized that oxygen normally has 8 electrons, and an oxygen ion therefore has 2 more negative charges. So we have 8 electrons plus 2 more is equal to 10 electrons. And so 10 electrons is the same number of electrons as magnesium ion. And so, in fact, oops, there we go. Our electron configuration should be actually identical. Oxygen ion has an electron configuration of 1s2, 2s2, 2p6 as well. Okay, so now what we've done is we've gone over the shapes of the orbitals. We've gone over how to go about writing electron configurations and drawing orbital diagrams. We've gone over the Hund's rule, Pauli exclusion principle, and the Aufbau principle. You should be now ready to complete the homework assignment that I gave you last week. So for homework due tomorrow, please finish that worksheet and we'll go over it in class tomorrow. Also, please remember that we have an exam on Thursday on Unit 2 involving atomic theory. If you have any questions, please email me and I'll see you guys tomorrow. Bye-bye.